Hey everyone, in this video, I would like to talk about how to deduce Gergonne's theorem for competition math. So here we go. So I need to give you another triangle and of course, concurrent point. Three Sevians must meet up at a point of concurrency. And I would like to just call this as A and B and C. And there's gonna be one Sevian and another Sevian and another Sevian like this. All right, so let's just try to mark this as D. And here's your, we got E and we got F. And of course, that's going to be point P. All right, so check this out. If I want to figure out certain area proportion, well, you know that triangle APB area to the whole thing, which is going to be triangle ABC, well, that turns out to be the same thing as triangle. Well, APB corresponds to this part, and I would like to say APC. So we got APC out there and out of ABC. And at the same time, if we have a triangle ABC, well, we get BPC out there. So BPC. And if you add them up, it all becomes one. So it's an obvious thing. We got just three slices of pizza that are all pairwise adjacent to one another, and it makes a triangular pizza, so to speak. All right, so that being said, I would try to change this area ratio into something that I know as a similarities. So I'll just show you a canonical picture and see what's up, all right? We know that BC is fixed out there. And if I simply drop the perpendicular foot, and if I drop another perpendicular foot like this, would you notice that triangle BPC, just try to focus on this ratio, and that's going to be true without loss of generality. We're going to have a similar approaches for the other fractions that we have. And BPC to ABC, well, it looks like the height ratio and another height, it determines the area. So if I just, just very specifically, if I just call it H1 and H2, we get 1/2 the area of triangle BPC. Well, it's just going to be 1/2 times BC times H1. And I would just like to call this the shorter height as H1. And you know that ABC, the triangle ABC, has the area of 1/2 times BC times H2. And of course, this H2 corresponds to the height of, height dropped from the altitude, the length of the altitude from A to BC. Okay, so if I, if I divided it out like this, then we automatically get H1 to H2. Now, remember what we've done for Menelaus? Menelaus told us that the height ratio for similar figures is just going to determine, it's going to be exactly equivalent to the ratio of hypotenuse. Well, we're going to do the same thing. Well, H1 to H2 is going to be dP to AD, right? So we have dP to AD. So using the same approaches, well, APB to ABC is just going to be PF to CF, right? So PF to CF. And that becomes the ratio of hypotenuse for an associated right triangle with the altitudes. And we have APC to ABC. That's just going to be PE to BE. All right, so PE to BE. And we're adding it up with the last fraction that we just investigated. The last fraction that we just investigated, looking at those very specific pictures about BPC and ABC, and that becomes a PD to AD. And this becomes 1, and this is how we showed and proved the Gergonne's theorem. Now, the Gergonne's theorem obviously uses the similarity ratio for the right triangles, and we're not just getting the height ratio. The height ratio was the intermediate process. We're just using the hypotenuse ratio, but height ratio was actually the essential part in proving the Gergonne's theorem.